Go
If you
ahead
just-
and stop the meeting.
Well, the meeting is recording. What would you like me to start with? It is 7:36, and this is the September 20th, 2023 meeting of the Astronomical Society of Greater Hartford.
That is great, John.
And I'm calling the meeting to order because Chris asked me to.
Okay. All right. Where is it going? Oops. Okay. All right. I'm not sure how many people we have on Zoom. We've got a nice turnout in the room for the people that are on Zoom. This is our first meeting of the 23-24 year.
We have 6 right now.
Okay, all right, I'm pretty happy with the way this is working. I wasn't sure this would all actually work out. You are on camera. That iPad in the corner has the room on camera. This is the camera that will be showing the presenter Ryan's presentation with us to be on Zoom. So there's cameras everywhere. You can't make a move without them. That is a conference microphone. Got a little red speaker in the back. John's in there, playing with all the other Zoom people. So I think we're good. Cables everywhere.
Except we can't hear you too well.
You can't hear me?
No.
You gotta speak up a little.
Oh, sorry about that. Okay.
Now
Cables
now
everywhere.
now we can.
Please watch your step. And that's it. Welcome. Thank you for coming. And we'll go ahead and dive right into the presentation.
So Scott Tracy and I represented ASBH at evaluating the CT Science Fair competition. And we reviewed, I think it was 16 projects that fell within a broad category of astronomy, cosmology, astrophysics, astromath, and stuff like that. And Ryan's project stood out with us, not because he did groundbreaking science. It's because he did science in a procedural and very deliberate way. I would just want to mention that before Ryan comes up, I want to welcome Ryan's parents and brother. Thank you guys for coming, and his mentor. Hopefully you can introduce yourself later on during the question and answer period. Also, I would like, with your permission, to make available your science fair material to the rest of the club. I can put it on to the group's IO shared site so that you can also get as impressed as we were by reading his paper and seeing his poster. The most important thing to tell you is that Ryan is a junior in high school, and he could compete favorably with the best science projects that we saw for the Connecticut Science Fair this past year. So I just want to tell you that how impressed we were with Ryan, and that he walked the footsteps of Kepler and Romer and did science that they did during one term, right? It was just one school year. That was 150 years of science that he did in one school year. And he's got quite a journey to share with us. So I'd like to introduce Ryan, bring him on up here to get me out of the way, and then good luck. Thank you. Enjoy yourself.
Ryan, can we have an audio check?
You hear me?
Very clear. Thank you.
All right. Thank you all for inviting me here.
You know, when you need the Excel.
Yeah, we just need to take the last chart. Do you want to go in presentation over? Yeah. Oh, sorry. No, down here. Yeah.
All right, this is a poster that we presented to the science fair with all its parts. We have 5 parts: conclusion, our future plans, and our references. And these are all the components of it. And we'll start with the shape and orientation of the Earth's orbit first.
What's this called again? Determining the size of the astronomical unit?
Yes.
Thank you.
All right, and that's so the purpose of this investigation is to determine the size of the astronomical unit using all of these components here. And our first part, we found this nice website here, and our goal was to analyze the average angular diameter of the sun, which we took pictures from this website here. And you can see on the left here, that's in January, when the sun is closest to the Earth, and on the right, yeah, when it's farthest. And we realized that the apparent change in the angular size of the sun is due to the distance change between the Earth and the sun. So what we did is we took those pictures from that website and we put them into Microsoft Paint, and we zoomed in really far. And on the very edge of it, we took the pixel coordinate. And then from that, we were able to make this graph. And you can see here that there's a significant dip, that it looks significant at least, but from the scale, you see it's only about 70 pixels. And on the y-axis, we have our horizontal diameter in pixels, plotted against the date. So we have from the 1st of January to the 27th of December. And it illustrates the measured solar angular diameter variation throughout the year. And here we have a little picture that helps us determine that the distance between the Earth and the sun is just the angular average diameter over the angular diameter of that day. And here we go to our script. All right, here is this is the Excel file that we worked on. And basically what we did is we have our data here, and we fit a model to it. And on the right, we have our root mean square error, which the lower it goes, the closer we are to fitting it to the actual data. So we just started plugging in numbers for these orbital elements. You can see how it changes. And so eventually, we just kept on plugging away. We got closer and closer to the actual orbital elements, which you can see they line up very nicely with this graph.
So what did we get from that? Oh, sorry, Ryan, what did we learn from that? Eccentricity.
Our eccentricity.
Click on resume slideshow.
Yep. And here is the measured shape and orientation of the Earth's orbit around the sun with its orbital elements. Our semi-major axis A, which we define as 1 AU. Our eccentricity of 0.0166 and our longitude of 103 degrees. And these are our results. We got pretty close to the accepted value from NASA. And then here's part 2 of the project. We have our relative size, shape, and orientation of the orbit of Mars. And here what we did here was similar to the Earth, where we were deriving our orbital elements out. So we have them here, our orbital period, the semi-major axis, the eccentricity, the inclination, the longitude of the ascending node, and our longitude of perihelion.
Right? Go back on slide. That's gonna tell them what we're looking at here.
Okay.
Read the captions.
So in this graph, we're looking at Mars and Earth in 2 consecutive oppositions, which we use to determine the orbital period. And this angle, the angle alpha, is determined in just a portion involving the length of the year and the degrees that the Earth moves throughout the opposition dates. And throughout this entire part, we analyzed 200 consecutive opposition pairs. And so we created this vector diagram. And from our earlier work, we have R1 and R2 because we determined the orbital elements of the Earth. And in order to get the orbital elements for Mars, we need the position of Mars, which we determined from this in our 2 unknowns, R3 and R4. We don't know their magnitude, but we do know their direction because from the NASA Horizons web application, we got the right ascension and the declination of Mars at the 2 opposition points. Here's just the 10 of our data points. And here, Professor Jaquin and I worked on a Python program so that we didn't have to do all these calculations out by hand because there are over 200 of them. So we were able to just put all of our data in and it would give us out our calculations for the 200 opposition dates. We have a graph here determining the inclination and the ascending node. So on the y-axis, we have our ecliptic latitude in degrees, and on the x-axis, we have our ecliptic longitude in degrees. And the orbital inclination is the
Maximum value.
yeah, it's our maximum value there. On the very top red circle with 1.85 / 9 degrees. And the ascending node there, the left circle, the left red circle. And here we determine the longitude of aphelion, our semi-major axis, and the eccentricity. And so this equation for the planetary orbit of a very low inclination we got from just Wikipedia. And theta naught is our ecliptic longitude of aphelion. And so that equation, we just rearranged it in a form where if 1/r, which is the y-axis, if it's plotted against cosine theta minus theta naught, or the x-axis, then a straight line will result. If and only if the correct value for theta naught is used in the equation. And so by an iterative process of replotting the values of theta naught, we determined that or we determine values of theta naught that can linearize the data. And once the graph is linearized, we have slope of, you can see there, we have minus e over, I think it's alpha or a times 1 minus e squared, and a y-intercept of 1 over a times 1 minus e squared. And then after that, just doing some more math, you can determine the semi-major axis and the orbital eccentricity.
Let's show them how it's done.
All right, here is similar to the one showed in the Earth part. We did the same thing, we just had a model. And we just started putting in values of theta naught until the line got, or the graph got linearized. So set it to 0. It looks like this. Go to,
Let's remind everybody what the axes are.
yeah, so the y-axis is 1 over r. And our x-axis is cosine of theta minus theta naught. You can see when you just start putting in more values, the graph gets linearized. So, there you go. Okay, these are our values that we got. All very close to the accepted values. And we have part 3, the identification of the Galilean satellites along with their orbital radii and periods. And this image here is a simulated daily image from the planetary program Stellarium. And it's an image of Jupiter and the Galilean satellites. And just very simply, we just got a ruler and measured in centimeters each of the satellites' distance from Jupiter in order to really determine which one was which. So a little more clear in this graph, you can see the red circles are Callisto, and our blue circles are Ganymede. And this is the first. This is the first 20 out of 39 days that we had. And here's a graph of Europa. This is the image distance from Jupiter in centimeters over time.
And what we use this for? We determine the.
Yes. And we use this to determine the period, and similar to everything else, we had our data and we created a model and just fit orbital parameters to it. See which one fit the best. And we did the same thing for Eo's orbit, but Eo's orbit is only 1.7692 days, which is very short, so we can't show it over time too well. So on the x-axis, we chose to show the phase. And looking at the red circles, you can see in the very beginning, they start below the black circles, and then towards the middle, they go up higher, and then at the end, they go back down lower. Professor Jaquin and I were a little confused as to why this was happening until we realized that it's probably due to the changing geometry between Earth and Jupiter.
Like, what are the difference between the black and red dots?
Is that just 2 phases?
Black circle for the first half of the data.
Yeah.
The red circle for the second half of the data. So
Yeah.
the time difference.
Yeah, so there is a time difference between the two observations. The black circles there were taken before the red circles. The black observations are our first observations, and the red circles were our second set of observations. And with time, you can see that the changing geometry between Earth and Jupiter changes up the values a little bit. And we didn't account for that. We kept the distance between Earth and Jupiter constant. And this is what we ended up getting. And we have part 4, which we measure the excess time and EO transits between opposition and conjunction with Jupiter. A little backstory. Ole Romer in 1696 did this procedure. He made precise measurements of a series of EO transits across the face of Jupiter. And when the Earth was moving away from Jupiter, the time between transits of EO became longer. And this excess time was due to the increasing distance between Earth and Jupiter, and that combining the excess time with the change in distance between Earth and Jupiter during the transit period would allow for a calculation of the speed of light. This figure here shows the change in geometry for the angle. So we have 113 transits between February 2nd to August 20th, 2003. And the time of the transit and the ecliptic longitude of Jupiter at that time, the transit were recorded. And at the time of the transits had to be corrected for a changing viewing angle as Jupiter and Earth moved in their respective orbits. And you can see these are just 5 of the massive horizons data that we used, but we had over 110 that we ended up analyzing for the excess time. And this graph here, we have the excess time in minutes over the change in distance between Earth and Jupiter. And we only show the linear data in red here because at the end, it curves up a little bit, and we're just not too sure as to why it has that curve. So we took our linear data, and from this graph, we can see that the slope of the linear portion of the graph is 8.136 minutes per AU. So there's 8.136 minutes of light travel time per AU. And that's when we started to actually measure the speed of light. So Professor Jaquin and I met up in the spring of 2022, and we measured the speed of light at Onondaga Community College in Syracuse, New York. And we found a paper by Zoltan Boros and Gregor Wies entitled Foucault's Method for Measuring the Speed of Light with Modern Apparatus. And it described how to use the rotating mirror, it described how to use a rotating mirror from a laser printer to duplicate the original speed of light measurement by Leon Foucault in 1862. And in the picture there, you can see that was our setup that we had in the lab. And this is basically the concept of it. So his rotating mirror technique was to reflect the laser beam off a very rapidly rotating mirror in a very brief time for the beam to travel to and fro. The high-speed rotating mirror has rotated sufficiently to reflect the beam at a slightly different angle from which it was incident. And knowing the angular frequency of the rotating mirror and measuring the displacement of the laser beam spot on the camera detector, we calculated the speed of light. So this was the spot that showed up on our Logitech camera chip. And we created another Python program that kind of decompressed this image vertically, and that we were able to vertically integrate the spot image intensity and produce a single line intensity profile of the spot. So you can see here that at the different frequencies, you can see it moving. It's slightly tilted to the left a little bit. And that's our integrated Y intensity plotted over the pixel coordinate. And here is a graph of the laser spot position as a function of the rotating mirror frequency. And from this, we see that the magnitude of the slope is inversely proportional to the speed of light. So we're able to use this to calculate our speed of light. And with measured speed of light, Professor Jaquin had done 6 earlier determinations, and just to minimize any error, we decided to average all of our measured speed of light. And we got 2.959 times 10 to the 8th meters a second, which is just over 1% from the accepted value of the speed of light. And at the end, after everything we've done, we decided to calculate the length of the AU. So given the time we found for light to travel 1 AU in our analysis of EOS transits and the adopted speed of light from me and Professor Jaquin's determinations, we determined the length of the astronomical unit by simple arithmetic. And you can see there what we did in order to get the AU. And our derived length of the astronomical unit just came out to be less than 4% different from the accepted value. And we have our future plans here. This figure here is stars above and below the sun. And it's plotted over the galactic Z in parsecs over the galactic X in parsecs.
Where did you get the data from this?
This we got the data from NASA's Gaia project, I think it is, that they're doing. So we were able to go in and extract all these stars. And in the future, we plan to create kind of like a 3D visualization for this.
And why are we looking at this? What's the significance?
This is the galaxy, right?
The top?
This is the top and the bottom of the galaxy that we're looking at, which is really cool because I've never really seen a figure like this before, where you can see the top and the bottom of the galaxy and all the stars.
Is that a complete 360-degree reference?
Yes.
Yeah, 500,000 stars. Roughly.
Yeah.
Huge. And it's only 100 parsecs, but this is only 40 parsecs for us. We're working with a slightly larger data set of 100 parsecs, so like 300 light years square column. Who did just get a galaxy to the sun at the center?
Yeah. And that's the end of the project. Here are the references that we used. To do questions then?
All right, I have one.
Okay.
I know you measured the percent of deviation from the expected standard, but do you have the actual standard deviation in your calculations?
Or standard deviation for what particular variable?
For reference for your results compared to the standard 1 AU.
Flip back to our whoa,
The very beginning.
Or,
no,
or are your percentages or the actual standard deviations as percentage?
what I think if we look at the excess time chart,
Yeah.
that let's see, the AU was calculated really based on the slope of this excess time graph.
Yeah.
So as you can see, it's not perfectly linear. So there would be some uncertainty. There would be some uncertainty in that slope, but we did not. We did
Correct.
Not
There is ellipticalness to take into effect. I guess should have rephrased that as per a given date and time, but that would have been impossible to actually put into a science project. I withdraw the question.
So Ryan, why did you, in the process of trying to determine the astronomical unit,
Yeah,
why did you go to Mars rather than going directly to Jupiter?
we went to Mars just mostly for its history. We could have done the same thing that we did for Mars with Jupiter.
Okay.
And
One more forward. There you go.
this here, yeah. We could have done the same thing that we did for Jupiter. Or for Mars with Jupiter, but the history behind what Johannes Kepler did with Mars was very interesting to us, so we decided to take his approach at it and just learn the history of it all. And then instead of doing this all over again for Jupiter, we just decided to use what NASA had for Jupiter and instead switch it out for Mars. But it was just really cool what Mars had, or the history of Mars. And that's why we chose it.
We figured our analysis, it took quite a while, would have just confirmed what NASA had calculated.
Yeah,
That was a little bit difficult.
yeah,
Since we did so well with Mars, we figured they would get it now.
yeah.
Did you get to see any of Kepler's observational data? Where I'm going with that is, could you characterize how the data that NASA that you used looked compared to what Kepler used? What did you think when you saw that?
We didn't actually look at Kepler's data.
Yeah, I think
I've read papers on it, and one of the advantages we had over Kepler was a much longer time span. He had 20 years of data, we had 200 years of quote data. His data was just naked eye, so it was like 10 arc seconds. 10 arc seconds, 10 arc minutes, 10 arc minutes, I forget. It was just naked eye stuff from Tycho Brahe's naked eye observations.
Yeah.
And we had data that was perfect, to like 18 decimal points, because it was really a model. In some sense, what we did was a bit of a dodge, because we were just verifying a model that was used to calculate the data. But we wanted to go through the experience of just learning about the math, learn about the history of how the observations were made. How did we figure out our place in the solar system?
Yeah.
There wasn't just a recent paper, I apologize for interrupting. They compared Kepler's work with what similar to what we did, and what the modern is better.
But it's still amazing the measurements that Brahe did.
Yeah.
And then Kepler was able to kind of go through them all and figure out, okay, there's a pattern here, and he broke it out.
Yeah.
And we had the benefit of history to tell us we knew what the solution was. Kepler didn't know what the solution was.
Yeah.
He didn't know that the orbits were elliptical. They were also constrained by the Aristotelian idea that everything was circular. But his results showed that wasn't true, but he didn't know whether it was a shifted circle or what particular geometric shape. I think it took him 15 years to figure out that the orbits were elliptical. And if he hadn't tackled Mars, he might not ever have found it, because most of the other planets had very low eccentricity. Mars is about 9%, and the other planets are much less, on the order of a few percent or less.
Ryan could come back in 14 years.
What? Pardon me?
I said Ryan could come back in 14 years.
Yeah, have you published your findings anywhere besides the Science Fair Summit?
No, we haven't. We just, it's only been through the science fair project.
We would be interested. So, it was when we started this project, we didn't really know where we were going.
Yeah.
We started just looking at the angular variation of the sun and by if we defined an AU as whatever distance it was from the sun had its average angular size, that's where we started. And so if we go back to the first couple of slides, our purpose was to just determine not the size of the AU, but just the shape and orientation of the Earth's orbit. All we got from the sun was the Earth eccentricity and longitude perihelion, the ecliptic longitude perihelion. And even with Mars, we still didn't know how big an AU was. So when we got the relative size, we could tell that Mars was on average 1.52 AU away from the sun, but we still didn't know how big an AU was. And we didn't, so we kind of wandered along, and then we got thinking, well, if we could do rover work, by looking at the time discrepancies with the transits of Io, we could actually figure out how big an AU was, but we would have had to measure the speed of light, which Rover, of course, didn't have that opportunity. But before we could analyze those transits, we had to figure out which satellite was Io. So that led us to just looking at 39 days of consecutive quote pictures from Stellarium and really just trying to identify. We could have put the labels on the pictures and see what was what.
Yeah.
But we worked it out like Galileo worked it out. It was fun. Yeah, it was fun. And the ones we couldn't work out, we fit a sinusoidal model to the position of the satellite. And where we couldn't figure out which dot was which satellite, well, we fit the model to what we could, and then we go back and say, oh, this must be Europa and that must be Io.
Yeah.
So it was a real iterative process.
What was the biggest surprise that occurred to you as you went through this journey?
Biggest surprise. I don't know. I mean, I guess it was surprising how back then those guys did it back then. Like now we have NASA and stuff, and we have the internet to look all this stuff up. But I mean, I guess the time it took to create or to make observations, and then the time it took to do all those calculations by hand. Like we had the Python program do it all for us. Doing it out by hand was took probably like a year. I don't know.
Years.
Yeah. That's what surprises me, that those guys were able to do that. And get the answers that they did get. And kind of pave the way for us now.
What surprised me is it worked. I really, we walked into this not knowing what would come out when we actually got to the end, or how big would the AU would be. And we tried to stay as close to imagining that we had an observer friend that could make all the measurements from the telescope and then just give us the data. So we tried not to look anything up. Yeah. And we did pretty good with that. We had a little trouble with Io because our period of Io was not quite, even though it was like 1% accurate, it still wasn't accurate enough to get the excess time right. The tiny error in the Io's period that we derived. And I think it was because, as we mentioned, let's look at that slide, that when we tried to fit the orbit of Io to the orbital phase, there are those pairs of dots that were one above the other.
Yep.
That shouldn't have happened because we were working with essentially perfect data. Although we had to measure with a ruler, but there was a systematic error there. And I think it's because the Earth was moving towards Jupiter. So the latter half of our observations, the Earth was a little closer, so the orbit looked a little bigger. And that's why the amplitude of the red dots are a little larger. But we never had a chance to go back and work that out.
Yeah.
What's the time separation between the observations?
One day.
Yeah, not long at all.
Yeah, one day. And that's why we couldn't, if we flip back, we couldn't do this sort of fit.
Yeah.
Where we could just adjust the period of the sine curve because it was so tight that it would have been very difficult to sort it out. So I said, well, let's instead of look at time on the independent axis, let's look at the orbital phase. And observations come back on top of each other. And again, it was trial and error, flip overs. And we just had to guess that best fit period was arrived at by trial and error and minimizing the difference between the model and the observation. So again, minimize the root mean square error.
So why not use more observations?
Well, I think the problem is that the geometry between the Earth and Jupiter is changing.
Yeah.
So as we only see.
I don't think we
I
can
get-
for that, no?
I get real
It's like
excited.
constant.
At some point in the image, just flip back to the image. There you go. These images, so these are like simulated photographic images that we pulled out of still area. And we put the little circles on and we identified which moon number 1, 2, 3, 4 was, and we just kind of had to figure it out. And you probably can't read the numbers, but in the little black boxes are the date and time. And we took these simulated images were midnight on 39 consecutive days. So, but what's not in there is any angular scale. So we have no way to convert the distances, the centimeters that we measure on the image. We need to convert those into a real length, a real kilometer, hundreds of thousands of kilometers. So we need an image scale. So on one of the slides, we don't show it here, there are 2 stars that appear in the upper left and lower right. And we can look up the rate ascension and declination of those 2 stars, and therefore establish an angular scale, like that many centimeters equals that many degrees. And once we have an angular scale, then we can turn all those centimeters, if we can turn those centimeters into real life kilometers, if we know the distance to Jupiter. But we just used one distance from like the first day, and in retrospect, we should have, in order to make the calculations, we should have updated the distance every day.
Yeah.
Yeah, so it was a little shortcut that we didn't realize would have the impact it did until we looked at this and said, it should be better.
Yeah.
Yeah.
When I'm using the excess time of the transits to calculate the distance of AU, did you let the Earth complete 1/2 orbit, or was there a slightly less than a half orbit?
Let's go to the orbit figure. We started our observations. Back. Forward. There.
This one here.
There. We started our observations when Jupiter was at 0.1 up there, and the Earth was at 2. So we started in opposition.
Yeah.
And that little circle around Jupiter is Io, and it's transiting, but it passes right between the Earth and Jupiter. And then the Earth would move counterclockwise around its orbit to 0.4 at the bottom. And meantime, Jupiter would more slowly drift around its orbit to 0.3. So we went from opposition to conjunction, or near conjunction anyway. And in that time period, from opposition to conjunction, there were 113 transits. And what we did is we recorded the time of each transit that we would have gotten from our secret observer friend, what we actually got from NASA's Horizon web application. And then just compared it to the orbital period. And it was always just a little longer, that the observed time between transits was a tiny bit longer than the orbital period of Io. Partially because the distance was increasing between the Earth and Jupiter, so it took longer for the light to travel. But there was also a big correction we had to make. As you can see in where Jupiter is at number 3, the transit occurs on that diagonal line.
Yep.
But we should really be measuring from the vertical line there, because that's the same geometry. So we had to calculate what that angle alpha was, and we did that using the ecliptic longitude of the Earth and actually the ecliptic longitude of the sun, it's a longitude system, ecliptic system centered on the Earth, and the ecliptic longitude of Jupiter, you can figure that out a little bit.
Yeah.
So, and that was actually a big correction. And we were still left with like 14 minutes
Yeah.
of excess time. It should have been 16 minutes, but we got 14 minutes. Roughly.
I'm wondering how you two connected with each other and how you decided on such a project.
That's great.
It was at a bar in New York. I wasn't drinking, my parents were.
We
Yeah, fine.
Our oldest son, is finishing college this year. He was playing collegiate baseball in the state of New York.
Yeah.
And we're into a brewery and Ryan and his little brother were playing chess. And this fine gentleman was sitting at the bar and we started talking, and the rest is history.
Yeah.
You're a little bit of a craft beer.
You will pass off and I am a physics and astronomy professor, emeritus now, semi-retired, and I'm talking community college. It beats working for a living. Although yesterday.
Where do you go to school, Ryan?
I go to Wamogo Regional High School up in Litchfield, Connecticut.
That's where he wants to go to college.
Actually, I couldn't tell you that.
He doesn't know yet. We're working on that.
That's okay. That's okay.
You got a great school wherever you want to go. You're really wonderful. Thank you so much. for Yes,
Feel free to, Ryan's poster for the science fair presentation is just over here on the wall behind you, so anybody can look at it on the way up. Feel free.
Dr. Jaquin herself has some intensive credentials for your humor skill. Where you guys doctor.
Just for the occasion, I wore my smart shirt. I did my graduate work, I wore my smart shirt, so I wouldn't say anything stupid.
You also have been like, super.
All right, we're gonna continue here.